And in this part, there we go. Now in this part, we are going to look at the solid state. Solids, it depends on the way solids form and come together. We can classify them into two major classes. If we have some kind of a repeated geometric pattern to the arrangement of particles of the solid, such as we see here in this figure, then we call that solid a crystalline solid. But if the arrangements are random, like we see here, then it's called amorphous solid. We are not going to focus on an amorphous solid in here. We're going to look simply at crystalline solid. They're much more interesting. And we have four types of crystalline solids: ionic, molecular, covalent, and metallic. And in the next table, you'll see what we're talking about. For ionic solid, the type of interaction that hold them together is ion-ion. That means the individual particles that make up an ionic solid have to be a cation and an anion, such as potassium nitrate, sodium chloride, or magnesium oxide. As a result, those interactions are very, very strong, these electrostatic interaction. They're going to lead to high melting point. These compounds, because they're ion-ion interaction, they can lead to ion-dipole interaction. So they're generally water-soluble, they're brittle, and now, we don't really talk about them in terms of conductivity much, because in the solid state they don't conduct. So since we're not talking about the liquid state of these, then we're not gonna even mention if they conduct or not. Molecular solids, on the other hand, they are made of molecules, and molecules are held together by intermolecular interactions, such as dispersion forces, hydrogen bond, or dipole-dipole. So as a result, they have low melting point, and most of the time, these solids are non-polar, therefore they won't be soluble in water, and they'll be soluble in organic, and they are insulators. Regardless of what state they are, they're insulators. Network solids, on the other hand, they're held together by a network of covalent bonding, hence the name network. As a result, you have very high melting point. They're insoluble in all solvents. They're brittle, and they are insulators. And last, metallic solids. They're made of individual metal atoms, and they have wide range of melting points. They are insoluble, and they're malleable, ductile, and good conductors of heat and electricity. Now, malleable and ductile, it means we can deform them whichever way, and they will maintain their properties. Let's take a look at them in a little bit more detail. Molecular solids, they're made out of individual molecules. They're held together by these individual intermolecular interaction, and they have low melting point. Some examples of these would be solids of benzoic acid here, or glucose. You have like a network of intermolecular interaction. They really don't have. So all I need from you is to recognize what those solids are. Then we have atomic solids, and they come in different variety. We have non-bonding atomic solids. This something like, for example, noble gases. Even though they exist in the gaseous state, if we were to decrease the temperature drastically, they would form a very nice packed solid like this. You can ignore this part. You don't need to know. Just know that they're held together by dispersion forces, and they have a very low melting point. The second type of atomic solids are network solids. These network solids are held together through a network of covalent bonding. As a result, you get really hard solids. All right? Now, and bonding patterns determine the property of the solid. So I'm going to give you one example of this, and that would be network solids of carbon. And I'll give you two allotropes of this, diamond and graphite. Diamond and graphite are made out of solely carbon atoms. The one carbon atom in diamond have 4 carbons attached to it. Therefore, you have a tetrahedral geometry around every carbon. Whereas in graphite, we have a double bond. So you have three things attached to it. Let me go back here. In the graphite, you have three atoms. So if I take this one, two, three, only three atoms. If you have a double bond, one double bond, then you will have a trigonoplanar geometry. In the diamond structure, because of the tetrahedral nature of the geometry, the growth is going to be in 3D. Whereas in graphite, the growth will be in 2D only. And in order for us to see the 3D structure, the layers are held by intermolecular interaction, London dispersion forces. That's why graphite is much weaker than diamond. Then we have atomic solids, metallic atomic solids, and those are held by metal interaction, and there are two prevalent models. Your textbook describes only one model, which I already talked about in a previous chapter, so let me give you a quick review. Your textbook talks about those metallic elements. They shed their valence electrons and they exist as cations in a sea of electrons. I don't like that model, but nonetheless, that's the one your textbook talks about, so we're sticking with it. And also, we talked about existing in metal alloys, and there are two types. This is just a review. I already told you about this. So you can replace some of the metallic elements here by another with a similar size. So for example, if I take copper and replace some of the copper atoms in here with zinc, we can come up with a brass alloy. This is known as substitutional alloy. On the other hand, if we were to fill the holes that are due to the stacking of these spheres of the metal atoms of iron with carbon, much smaller one, then we end up with interstitial alloy, and that's how you make steel. The last type of solid we're going to look at are ionic solids, and these are made of individual ions. Bonding in ionic solids is non-directional. What it means is, if you take one cation, let's focus on this one in the center of this cube right here, it will interact with 1, 2, 3, 4, 5, 6 chloride. Non-directional. One cation interacts with 6 chloride anions. And if you look at the chloride, if we were to put it in the center, you would see that it's interacting with so many others. So if we take this one right here, it's interacting with 1, 2, 3, and if you expand this and put another cube next to it, you'll see there are another 3 cations that it interacts with. That's what bonding is going to be, non-directional. And this is a summary of crystalline solids. You guys can, you have this graph in your textbook and you can reference this one. The last part of this chapter, I'm going to talk about phase changes. And there are 6 phase changes, and each phase change is either endothermic or exothermic. Let me list them for you. The endothermic ones first, then we'll talk about the exothermic, and you need to know what each. So if I go from solid to liquid, that's melting. In order to melt something, in order to melt a solid, I need to input energy. That's why it's endothermic. If I go from liquid to gas, that's vaporization. That's also endothermic. And if I want to take a solid all the way to the gaseous state without going through the liquid state, this is known as sublimation. The reverse of sublimation is deposition. Condensation is going gas to liquid, and freezing is going from liquid to solid. The ones I have labeled in red are endothermic, and the ones I have labeled in green are exothermic. The heat that is required to change the state of matter from solid to liquid is known as heat of fusion. And the heat that is required to change matter from liquid to gas at its boiling point is known as heat of vaporization. Heat of vaporization is always much, much more than heat of fusion, because heat of fusion, you're loosening the interaction, whereas heat of vaporization, you need to completely break the interactions apart. All right? See how we're recording? Yes. Let's look at an example. How much energy is needed to vaporize 188 grams of a liquid if its heat of vaporization is 1.13 kilojoule per gram? So we're given the heat of vaporization. I'm given the mass. I'm given delta H of vaporization. And I can set it up as a dimensional analysis problem. Q equals M times delta H of vaporization. 188 grams times 1.13 kilojoule per gram. This will give me 212 kilojoules. All right, try this one. How much heat is required to melt 25 grams of ice at 0 degrees Celsius? You should pause the video and try to solve it and come back. You can look up the values that you need. All right, it's 333 joule per gram if you want to know the delta H of fusion. All right, so I have 25 grams, delta H fusion, 333 joule per gram. Q equals M times delta H of fusion. We set it up, and we end up with 8.33 times 10 to the 3 joules, or 8.33 kilojoules. Great. Now let's take a look at the following graph. This is a very, very useful graph. It's going to help us in calculation of how much energy is required to take a substance from one temperature into another. All right? What you need is for you to be able to sketch, interpret, and identify region in a graph of temperature versus energy of a pure substance over a temperature range. And in this case, you can go from below the boiling point all the way to above, below the melting point all the way to above the boiling point. All right? Usually you'll be given the mass of a pure substance, delta H of vaporization and or delta H of fusion of the substance, and the average specific heat of the substance, whether it's in the solid state in this region, liquid state in this region, or in the gaseous state right here, and you should be able to take it from one state into another. So let me walk you through what this means right here. If we go from left to right, this is known as a heating curve, and if I go from right to left, this is known as a cooling curve. So these curves are basically on the y-axis temperature plotted against input of energy, heat in joules, temperature in degrees Celsius. And usually this is broken into 5 regions: solid, solid and liquid, liquid, liquid and gas, and gas. If let's say we have a sample that we start in the solid state below its melting point. If I were to input energy, I'm going left to right on the x-axis. That means I'm adding heat. Then its temperature is going to change. Okay, let's say we have water and it's at minus 80 degrees Celsius. Ice at minus 80 degrees Celsius. If I add heat to it, it's not going to melt. I'm going to heat it from minus 80 all the way to its melting point, 0 degrees Celsius. We can calculate, we learned this in chapter 3, the heat, Q, the input of heat that is required to take it all the way to its melting point. We use the following equation, mc delta T. M is the mass of the substance, C is the specific heat capacity for the solid, and delta T is the change in temperature. So if I'm going from minus 80 to 0, which is the melting point of water, then that would be 80 degrees. Keep in mind, the process heating curve is endothermic. The cooling curve is exothermic. So when you calculate this, your value should always be positive if you have a heating curve, and your value should be negative if you have a cooling curve. Your sample is solid. You add heat, it will warm. until you get to the boiling point. Once you get to, melting point. Once you get to the melting point, any heat you input in there, it's going to be used to melt the substance with no change in temperature, and hence you have this horizontal line, no slope. When you have a slope line, that means temperature is changing in response to addition of heat. Temperature does not change in response to addition of heat, so you have a horizontal line. We can calculate, as we just did in the last two examples, m times delta H of fusion. That's Q. Once you have melted all your solid, it's completely liquid now. Any heat you add is going to increase its temperature until you get to its boiling point. We calculate the warming of liquid as follow. How much heat is required to warm it up? That will be mc delta T again. Once you get to the boiling point, then any heat you add should be used to vaporize the sample. So you have liquid and a mixture of liquid and gas in this region. You use m times delta H of vaporization. Then after you vaporized your sample, any heat you add will actually increase its temperature, hence the slope line right here, and you can calculate it mc delta T. So we use 1, 2, 3, 4, 5 different sections with 5 different, 1, 2, 3, same equation, 1, 2, same equation. So 2 different equations, but the constant will multiply them by. The C right here is different. Delta H fusion is different. This C is different. This delta H of vaporization is different, and this C is different. And you will see in the next slide when I use an example. When you're asked to calculate total heat flow, whether it comes in or out, it doesn't matter. The steps for you to calculate heat flow. Step 1, you need to sketch a graph having the shape shown in this figure right here. This is the shape you need to see, that figure right here. So you need to refer to that one. You need to sketch this. Then you're going to mark the starting point and ending point for that particular problem. So if I'm given, let's say, liquid water at 45 degrees Celsius, this is my starting point right here. Let me actually label it. This will be my starting point. And if I want to take it all the way to 115 degrees Celsius, this will be my end point. So when I do delta T, it's going to be 100 minus 45. And right here, it'll be 115 minus 100. And I need to use 1, 2, 3 equations to do that calculation. All right, that's how it works. That's how you mark the beginning and the end. Step 2, you're going to calculate the heat flow Q for each step, for each slope and horizontal portion of the graph, starting all the way to the end point. Step 3, you're going to add them all up. All right, let me show you how it works with an example. What I'm going to do with this example, I'm going to give you all 5 regions, but what I said always works. You can have 2 regions, 3 regions, 4 or 5 regions. So let me show you how it works. Calculate the total heat transferred when 19.6 grams of ice initially at negative 12 degrees Celsius is heated to steam at 115 degrees Celsius. So step 1, I need to draw a graph, and I'm going to put my starting point. That's A, and point is F right there. So that means I'm going to go through all 5 segments. Segment 1, going from point A to point B, that means I am increasing the temperature of the solid until I reach the melting point. mc delta T, the mass is 19.6 grams, times the specific heat capacity for ice is 2.06 joules per gram per degree Celsius. Final temperature is 0, initial temperature is negative 12, so 0 minus 12, and I'm going to convert it to kilojoules. I end up with 0.48 kilojoules. It's positive. That's endothermic. I'm heating. Now I'm going to do it from segment B to C. This is completely melting. No change in temperature. So I don't have delta T, right? It's simply M times delta H of fusion. That would be 19.6 grams times 333 joules per gram. That's delta H of fusion. This is the mass. Then I'm going to convert it to kilojoules. I end up with 6.53 kilojoules. That's two segments. Let me do segment 3, C to D. From C to D, I have a slope line, and my temperature is changing, so I'm going to need MC delta T, but I need specific heat capacity for liquid, not ice. It's different. (19.6 grams times 4.18 joule per gram per degree Celsius). That's a specific heat capacity for liquid. My final temperature is 100, initial temperature is 0, and I'm going to convert it to kilojoules. So I end up with 8.19 kilojoules. That's to D. Now the next segment I'm going to do from D to E, that's vaporizing the sample, and there's no change in temperature. That would be mass times delta H of vaporization. 19.6 grams times 2.26 kilojoules per gram, 44.3 kilojoules, and I have one segment left, E to F. E to F, my temperature is increasing, so I'm going to use the mass of water times the specific heat capacity for the vapor, and that's different, 2 joules per gram per degree Celsius. Final temperature 115, initial 100, converted to kilojoules. I end up with 0.59 kilojoules. The last step is to add them all up. The amount of heat that is needed to take 19.6 grams of ice all the way to at negative, whatever it was, 12 degrees Celsius, all the way to 115 degrees Celsius requires all these 5 steps. So I'm going to add them all up. So I'll just add them up. 0.48 kilojoules plus 6.53 plus 8.19 plus 44.3 plus 0.59 kilojoules will give me 60.1 kilojoules. All right, so make sure, guys, you do end of chapter exercises on this, on the online homework, and if you have any questions, please come to me with these questions. And that's the end of this chapter.